time, they are candidates for implementation of quantum bits, and they show long appearance time even at room temperature. And I will show you how we use Newton scattering to characterize these systems, and at the same time to understand their relaxation dynamics, and and I will give you some recipes how to improve their performance, and I will go to the conclusions. So we know that for slow relaxation and magnetization in molecular magnets, we need, first of all, a large anisotropy barrier. And this was found first with manganese 12, which had an anisotropy barrier of 60 Kelvin and a blocking temperature of 4 Kelvin. And it took almost 25 years to go to blocking temperature above nitrogen temperature and liquid temperature in 2017. And there was a big jump from 4 Kelvin to 80 Kelvin. But we know that the recipes for slow relaxation is to have a large barrier, which means we have either large spin or J. We should have a large anisotropy, and most of all, we have to prevent relaxation, first of all, through the tunneling, or through the phonons and other means of relaxation. So we decided to, as I said, there was a big jump in 2017 where the dysprosium-based single ion magnet was synthesized by the group in Manchester, where they found that the hilarity loop opens at 60 Kelvin. And this has been achieved by using lanthanide ions, where we know that lanthanides have a much larger anisotropy, and that was achieved in 2017, and soon after in 2018, it was possible, another group synthesized a molecule which breaks the nitrogen temperature of 77 Kelvin with this molecule, again based on dysprosium, that shows a blocking temperature of 80 Kelvin. Both of these molecules, they have they're based on lanthanides, and they have a large anisotropy, in particular, a large anisotropy barrier. In particular, the dysprosium has a barrier of 1,700 Kelvin, and the more recent molecule of about 2,000 Kelvin. And this seems to be the recipe then, but of course this is not the case, because, for example, another molecule synthesized very similar to those two, with even larger of the one at 60 Kelvin anisotropy barrier of 1,800 has only a blocking temperature of 4 Kelvin. So this tells us that the energy barrier is definitely not only the only figure of merit for this for having a large blocking temperature. So we decided to investigate in details what are the mechanisms of relaxation of the dysprosium molecule, which shows a blocking temperature of 60 Kelvin to start with. This molecule has an actual anisotropy along the z-axis, and the ground state is as J 60.5, and by ab initio calculation it is possible to calculate the energy level diagram, shown in this figure on the left, where we see that the top of the energy diagram corresponds pretty much to the effective anisotropy barrier of 1,700. Now, the first gap between the first ground state and the first excited state is at around 600 Kelvin, which corresponds to 57 eV. So, first of all, we decided to investigate if we could measure this anisotropy gap using elastic Newton scattering. And these measurements were done at ISIS using the Merlin spectrometer. And on the left, you can see the data. The blue curve is representing the dysprosium measurement. The green is the yttrium equivalent, blank, that enables us to remove the non-magnetic signal to extract the magnetic one. So by subtracting the blue to the green to the blue, sorry, we obtain the magnetic peak, which is around the 65 millielectron volt here. And this can be better seen if you look at the Q-dependence of these excitations. In fact, at 65 Kelvin, we see this intensity here that drops with Q, which is a clear indication of a magnetic excitation. The others are phonon excitations, which have a different Q-dependence. So we were able, therefore, to extract directly the position of the first excited state from the 15.5 to 13.5, which was predicted to be around 57 millielectron volt, and we found instead 65. So the ab initio calculations seem to be quite consistent with what we found experimentally. Now, not only we could measure the magnetic signal, but we also get the phonon signal, and this is a collection of data done at different incident energy, this colorful plot, where we stitched together different incident energy to obtain a full spectrum from around 0 to 150 millielectron volt energy transfer. We obtain these excitations, which can be then reproduced by DFT calculation. So on the top right here, you can see the calculation done, DFT calculation on Castep, where we have the density of states, but we have to weight the density of state using the neutron cross-section to obtain a spectrum that can be compared to our measurement. And this is done at the bottom here with this red curve. So you can see that the two spectra look quite consistent, and therefore we can confirm that the model is quite robust and can explain our experimental data. Now, given this model, it's possible now to collaborators in University of Parma, they were able to calculate the spin Hamiltonia, which contain the magnetic, the phonon, and the magnetoelastic term, and by calculating this and calculated the relaxation time, they were able to simulate the relaxation time as a function of temperature in this graph here at the bottom, and it is published in this paper on the right, on the corner. So by simulating the relaxation time, we can understand better what are the mechanisms that are driving the relaxation. And they can be divided into three different regions. At high temperature above 60 Kelvin, we have the Horvath processes, which are enabled by the presence of optical phonons, which are resonant with the energy level with different electronic excitations. And so they are promoting the relaxation at high temperature. If we go at lower temperature, below 60 K, we start to promote Raman processes, and below even lower temperature is the tunneling that drives the relaxation. Now, given this, how can we understand better what are the contribution of each term? And you can see that here, the black line here represents the relaxation, the fit of the relaxation data. And if we calculate the contribution from the optical phonon, is this light curve here, which doesn't contribute much to the Raman processes. As you can see, the black line is mostly represented by the green curve, which represents the contribution from from the acoustic phonons. So the Raman relaxation is driven by essentially by the acoustic phonons. If we go higher in temperature towards the Horvath regime, above 60 Kelvin, then it starts to kick in the optical phonons have a major contribution to the relaxation. Interestingly, if we have the crystal field splitting, putting half the value what is effectively it is, we obtain this curve here, the blue curve. So we see that the relaxation time decreases, and as we lower the gap between the first the ground state in the first excited level, and therefore this is also an indication that in the Raman process is also the distance between the two the levels of the crystal field is important to promote that kind of relaxation. So basically, we want to make sure that Raman is reduced in its efficiency, so that we drop these relaxation time to larger values by reducing the relaxation, the Raman processes, and so pushing the blocking temperature towards a higher temperature into the orbit regime. And this can be done by increasing the crystal field gap, because it has an effect also in the Raman processes, and also by decreasing the acoustic phonons and increasing the energy of the optical phonons, so making the molecule more rigid, so that we push this kink in the relaxation time to higher temperatures. So, given this understanding, we decided to analyze and study other different molecules, so to confirm our study. And to do this, we selected a couple of other molecules which have a larger anisotropy barrier, similar to what this dysprosium has. But to the contrary, with its dysprosium, the blocking temperature is much lower this time. So for the two molecules at the bottom, the blocking temperature is 7 Kelvin and 8 Kelvin, even though the anisotropy barrier is around 1000 Kelvin. So we wanted to understand better what are the mechanisms that lead this different behavior. And to do this, we recur again to the industrial neutron scattering first of all, to characterize the condensed states of these two molecules, and we use Merlin again. And these are the color plot are the measurement, and the red curve are the calculation, again, DFT neutron weighted data. And now, if we compare the bottom here in this figure, the density of state for the three different molecules, the black one is the curve corresponding to the 60 Kelvin blocking temperature, and the other two are the 6 and 7 Kelvin blocking temperature molecules. And you can see that the density of state is much larger for the two faster relaxing molecules, and also the steep of the curve of the acoustic modes, the low energy modes, is lower for the slower relaxing molecule with respect to the faster relaxing ones. So, given that now we have a robust understanding of the phonon density of states, again, it is possible to calculate using the speed Hamiltonian formalism the relaxation time for the three different molecules, and the continuous lines are the calculation compared to the experimental findings. And you can see that the calculations are representing very well the experimental data, and this gives us confidence that this kind of methodology is quite robust to understand the different mechanisms. And so also in this case, we can conclude that having a large crystal field gap with the axial anisotropy, which prevents the cross relaxation at the top of the barriers, is a good ingredient for having a large blocking temperature. And as we see from this density of state, as I already anticipated, we want molecules that don't have a steep acoustic phonon or low energy phonons that increase not so steeply, so that the blocking temperature is increased. And to do this, we want a weak link between the different molecules in the crystal lattice. And at the same time, as anticipated, we want the optical phonon to move up in energy and therefore reach the surrounding of the dysprosium ion and the ligands around the dysprosium. So this study was inspired us to go to study other molecules that also display different relaxation time, even though they have the same similar electronic structure. And this is the second example I'm going to talk about, is the vanadiol single ion quantum beats. These molecules have vanadium plus as a central magnetic ion, which is spin 1/2, and they've been very interesting in the last few years because they show, for example, the salicylene shows a coherence time of 1 microsecond at 300 Kelvin, so they are still showing coherence at room temperature, which is remarkable. And also these other molecule here shows coherence time of almost 1 millisecond at 10 Kelvin, which is also quite remarkable for molecules. We compare with as we saw already with the Eugenio Coronado, we compare the different behavior and different performances of these molecules. We see that the one with 1 millisecond coherence time is at the top of this figure, overcoming the coherence time of nitrogen vacancies in solid state, and also the VOPC also shows the highest temperature, coherence time at the highest temperature. So we are doing quite well as compared in the whole plethora of different proposed systems for quantum beats. Now, we decided to investigate also in this case different molecules which shows the same electronic structure but very different spin coherence time. And these are reported here on the left. There are 3 molecules that have different ligands, but the center and the core of the molecule is the same. So if we look at the phonon spectrum for these 3 molecules, you can see that the smaller molecule, of course, has a less dense density of states. For phonon density of states, we go to bulkier molecules on the right. The red density of state is very dense, and we can see that for a smaller molecule and a smaller lattice cell, there will be more possibility of a phonon bottleneck, where there are no phonons that can promote the relaxation, while it's more difficult for this larger molecule. And so this is giving already an indication that how can a phonon bottleneck promote long coherence time in smaller molecules. But what we did, we picked one of the series, and especially we picked the most simple one to study with neutron scattering, to have a more clear indication of the phonon dispersion. And this is the vanadiol acetylcetonate molecule, which presents a pentacoordinate vanadium 4 plus ion in the center, the green sphere here. Which is coordinated with the oxygen in the apical position, which has a much shorter connection with the much shorter ligand with respect to the oxygen at the basal plane, this square pyramid, which is quite distorted and therefore creates an anisotropy, and the orbital that is occupied is dxy, which gives with a single occupied orbital, which gives us a spin 1/2, and the others higher energies are much higher above the ground state, just above 1,500 millielectronvolts. So in the low energy part of the spectrum, we already have no magnetic excitation for this molecule. So we decided to look at the phonon dispersion for this molecule, in particular with neutrons. So if we look at what we see with Raman and infrared, we are limited to the gamma point. So while with neutrons, we can explore the whole dispersion in different directions, and also we don't have any selection rules as opposed to infrared environment, so we can see the whole plethora of phonon excitations. This is a neutron scattering cross-section for phonons, so just complicated, but I would just wanted to focus on the fact that we can extract the energies of the phonons and also their polarization vectors, which by a careful selection of the momentum transfer of the neutron Q, we can pick transverse or acoustic phonons and so separate the two, which is the beauty of neutron scattering as well. So by calculating this polarization vector and the energy to the FT calculation, that we can now plug it into this formula for the neutron cross-section, we can then compare our experimental data with the calculation, the FT calculation. And the measurements can be done using the most advanced neutron spectrometer, for example, LTE DISIS, which deploys these position-sensitive detectors that allows a four-dimensional map, as we did also for magnetic scattering, in QX, QY, and QZ and energy. And the same we can do with phonons, so also the mapping of excitation as it is done here for antiferromagnetic waves. We can also do the same for phonon dispersion. And that's what we decided to do with the vanadium acetate molecule. We need large single crystals, so there have been we have to align 40 small crystals that were synthesized by the group in Florence of Roberto Sessoli, and we need also the deuterated crystals because hydrogen creates nuclear background in our data, and by using LT, which has a large detector bank, we can explore a very broad and wide Q range in the reciprocal space, and also we have quite a good resolution in energy to be able to separate different, as we see that it's quite dense phonons density of state, we can separate different energies by using high resolution measurements. And these are the measurements that we perform. The top is the data, and the bottom is the calculation using the FT data, the FT calculations. And you can see that we can extract a lot of, we can measure a lot of different direction and modes. Depending on the incident energy, we can extract, we can go a higher resolution or lower resolution, and the calculation to match quite well our experimental findings. This is then the phonon dispersion curves, and the calculated one as compared to the red dots, which are our fitted values, and you can see that we can capture most of the excitation at most of the phonons at low energies. And finally, what we observe is that there are some acoustic modes that start from the gamma point and go up to 3 MeV, which are start to cross with the optical phonons coming down from higher energy. And this anti-crossing, which appears at around 3 or 4 MeV, is quite relevant because the optical phonon have a very strong spin-phonon coupling as opposed to the acoustic ones in the system. And this means that by this anti-crossing, the acoustic phonons start to have more optical character, and they can promote more relaxation at this at lower temperature. And so this tells us that if we try to increase the energy level of the energy of the optical phonons and avoid this anti-crossing, we can maybe decrease the relaxation and therefore have a longer clearance time. So in conclusion, I've shown you how we can use neutron scattering to characterize either the phonon density of states or the phonon dispersion of two of the major molecules that are interesting at the moment in terms of slow relaxation and quantum Higgs applications. And I've shown you how we can use neutrons to validate the model of the DFT calculation, and this gives us confidence that we can use the model to then calculate the relaxation dynamics. And from the calculation of the relaxation dynamics, we can infer what are the major contribution to the relaxation and what are the ingredients that can help to make this molecule more robust and having slower relaxation or longer clearance time. And I've shown you how we can use neutral scattering very effectively to look at the dispersion curves of phonons. This is the start of, it's never been done before, it's the start of this process and of this study. And so I kind of encourage you to use this technique to look at the details of other molecules if you are interested to understand better how the relaxation is driven. And finally, I would like to thank all my collaborators, in particular the group of theoreticians at the University of Parma, which has been very strong. We have a lot of strong collaboration. It has done all this very difficult calculation, and the group of San Vito and Trinity College as well, that did the DFT calculation, together with the group in Manchester, which produced also some of the samples, and the group of Roberta Sessoli in Florence for the vanadine molecule, and finally ISIS for providing neutron beam time. And thank you all for your kind attention.
And I wanted to ask a question about the last part, something about the experimental setup of how you measure with the single crystal. It's really, I had seen something before because from you and from Elena Kahachi, and it's really, really very interesting how you do this. But I have some question about how the importance of preparing the sample with this kind of measurements with RNT and single crystals, because you work with you said 40 co-aligned crystals that makes about 1 gram. So you have about single crystals of 25 milligrams, and in this category you need a large sample. And how important is to have a good alignment of these single crystals, or you?
So in this case, the dispersion broadening depends on the co-alignment, but because of the intrinsic broadening of each crystal, so in terms of energy, in terms of Q, they are not so broad. So having not a good alignment, it broadens the signal in Q, and also in energy as a reflection. So it has, we had quite not so good mosaicity because of the difficulty of co-aligning these crystals. They were very delicate and they degrade, and so it was kind of a challenge. It didn't jeopardize the experiment because we still can see dispersion, and it's just it's certainly broader than what you would expect with one single crystal. Of course, it would be better, but so if they are within 2 or 3 degrees of mosaicity, we had 2 crystals that were off. So at the end, those were, but the intensity of those were not so, because out of 40, maybe 3 or 4 were not so well aligned, but we were within 3 or 4 degrees in the mosaicity. So it is important, it's not extremely important, but yeah, within that kind of degrees, it's still a viable experiment. I wouldn't go up larger than 3 or 4 degrees in the mosaicity in the cube. Yeah.
So it's enough just to distinguish these caps in the following spectrum, so you can be sure that you observe that those gaps predicted by theory.
In energy, you mean the anti-crossing gaps?
Yeah. Even with that small dispersion in your equation of single crystal, right?
Yeah.
Okay.
But yeah, so we had so many, so you can do better if you have fewer, of course. But,
Okay, thank you.
yeah, that's a good question because the anticrossing gap is quite small, and then the larger the mobility and the more broad it becomes, and it becomes more difficult to distinguish. Yeah.
Thank you, Tatiana. There are.
Thank you very much.
So my question was just about the size of these crystals, because you said you are coaligning 40 crystals. So I was wondering what is the total size of these crystals?
So it was 1 gram in total. Each crystal were about maybe 2 or 3 millimeters, like 2 by 2 by 2, maybe. So the weight was small, but in total, the total mass was 1 gram. But we did measurements on smaller mass, like half a gram of mass. That's the minimum I would go for 5 to 7 days experiments on the neutron high flux machine.
Okay. Thank you.
You're welcome.